Hi, hi everybody. This section 2.5 is applications of matrix operations. So we learned all this cool stuff about matrices in chapter 2, multiplying them and all those kind of awesome things. And now we're going to learn some applications, the practical real-world applications. So there's a whole bunch in section 2.5. I'm actually only going to make videos on the first two, stochastic matrices and and cryptography, encoding and decoding messages. So this video today, this video right now is going to be about stochastic matrices. So the first thing I learned, which I never knew, is that it's pronounced stochastic, not stochastic. I never realized that, but learn something new every day. Anyways, what is a stochastic matrix? Funny you should ask. Well, first I have to give you like a little introduction to it, and then we'll see what it means. So a lot of times you have applications that involve finite states. Not a state like California is a state, but a state like, for example, the residents of a city, some live in downtown, some live in the suburb, some live here, so that's called like a type of state. Like, am I a downtowner? Am I a suburban? What am I? Voters, you may have a look at voters. Some might be Democrats, some might be Republicans, some might be independents, some might be whatever. Soft drinks, some might be Coca-Cola drinkers, some might be Pepsi drinkers, some might be whatever other brand drinkers, and so on and so forth. So these are called the different states. If you're a Coca-Cola drinker, that's a certain state. And if you're a Pepsi drinker, that's a certain state. So we're looking at the probability that a member of the population, the overall population, is going to change from one state to another state. In this case, the jth state to the ith state. And that probability is represented by the number Pij. So Pij, if Pij equals 0.3, that means a 30% probability that the guy is going to switch from J to I. If it equals 0, that means the guy is loyal, he's staying where he is, ain't moving. If the probability is 1, that means he's definitely going to switch from this to that, whatever reason. So we can make a matrix now. So S1, so let's say I have a bunch of states, whatever it is. This could be Coca-Cola, Coke, Pepsi, whatever, Democrat, Republican, whatever. Red car, blue car, white car, whatever, gray car, whatever kind of car. It could be a lot of different things. So the probability that so if I'm in this first column, so I'm an S1 kind of guy. So the probability that I'm going to switch to become an S2 kind of guy, that's the number that goes in this entry right here. There is the jth state, so P21. So I is 2, J is 1. So the probability that I'm going to go from P1, which is this column, whatever that guy is, to go here, Zoe. So that's the probability. Anyway, this matrix that we have in front of us is called the matrix of transition probabilities, because it gives a probability of each type of transition or change within a population. And at each transition, each member in a given state is either going to stay there or he's going to change. So for example, P22 is the probability that somebody who's in state 2 is going to remain in state 2. Again, by state, I don't mean states like New York, Oklahoma, I don't mean that. I mean states like the state of having a poodle versus a Labrador versus no dog versus whatever, that state. Think of it as status instead of state, whatever you want to put it. Anyway, clearly, if you add up all the numbers in any one column, if I add up P11 plus P21, so P11 means the probability that this guy here is going to stay in state 1. P21 means the probability he's going to move to state 2. PN1 is the probability he's going to move to state N. Now, by the way, state N might be I'm going to become whatever, not have a dog at all, whatever it is. But we're listing all the possibilities here. So the probabilities have to add up in any given column, have to add up to 1. That's what we're saying over here. Oops, the probabilities in any given column have to add up to 1, because I'm going to do, because there's a 100% probability I'm going to do something. Either I'll stay where I am, either I'll move to something else, either I'll change all this, all that, whatever. So this matrix where all the columns add up to 1 is called a stochastic matrix. And that's the official definition. The official definition, an n by n matrix P is a stochastic matrix when each entry is a number between 0 and 1, because you can't have more than 100% probability. You can't. Probabilities has to be between 0 and 1. And the sum of the entries in each column of P is 1. So just to give you an example of a couple of stochastic and non-stochastic. So A and B, in this example right here, A and B are stochastic because that's, well, 1, 1, 0, 0, that's a bunch of ones. 0, 1, 0, obviously these columns all add up to 1. That was easy. A half plus a quarter adds up to 1. A third plus 0 plus 2/3 adds up to 1. By the way, the 0 here means that the person in this state 2, whatever state 2 represents, there's no chance that this person is going to stay put. This person is either going to move to, clearly this person, there's a 1/3 probability that the person is going to move to state 1, or the 2/3 probability that the person is going to move to state 3. But the person in state 2 is definitely not going to move. And by the way, I'm talking people. It doesn't have to be people per se. It could be other, these could be other things. It could be, I don't know, chemical reactions. So no, I have no idea. I'm just saying it could be whatever. So now matrix C and D are not stochastic because they don't add up to. You see here, 0.1, 0.2, 0.3. These numbers do not add up to 1. So matrix C is not a stochastic matrix. And matrix D is also not, because 1/4 plus 2/3 does not add up to 1. 1/2 plus 1/3 plus 1/4 actually adds up to more than 1. So that's so A and B fit the bill for a stochastic matrix. C and D do not. Notice, by the way, that matrix A, as you notice, looks like the identity matrix, and that's kind of fitting here because the 1 here means that the person in state 1, there's a 100% probability they're going to stay in state 1, and there's no chance that they're going to move. And here we see the person in state 2 is going to stay. That 1 means they're going to stay 100% in state 2, and there's no way that they're going to move, and so on and so forth. So it's kind of funny how this just means matrix A represents that everyone's a situation where that everyone's going to stay, everyone's staying put, nobody's moving for whatever reason. Alrighty, let's look at some examples of this. So we're going to do example 2, which is a consumer preference model. Okay, so there are two satellite companies, and they serve a city with 100,000 households. And this shows the figure. Now, this figure here shows the change in satellite subscriptions each year. Now, Company A right now has 15,000 subscribers. Company B has 20,000 subscribers. So there's still 100,000 people total, which means there's more people that you can get hooked up. Anyway, how many subscribers are each company going to have in 1 year? So this says here, if you're an A, there's a 70% chance you're just going to stick with A. There's a 20% chance you're going to go from company A to company B, and there is a 10% chance that you're just going to give up satellite TV altogether. If you're in company B, there's an 80% chance you're going to stick with B. There's a 15% chance you're going to migrate over to A, whatever reason. And there is a 5% chance you're going to give up your satellite at all. If you're one of these people who doesn't have satellite TV, there's a 70% chance you're going to stay that way. And there is a 15% chance you're going to get satellite B, that you go to satellite B, and there's a 15% chance you're going to go to satellite A. Notice that it's 100%. If you have no satellite, either you're going to stay that way, or you're going to get from A and B. Apparently, those are the only choices. But notice 70 plus 15 plus 15 adds up to 100. In fact, all of these, if you add up the choices, they add up to 100. There's 70% chance you're going to stay with A, 20% chance you're going to go to B, and a 10% chance you're going to go to nothing. So 70 plus 20 plus 30 is plus 10 again is 100%. But we want to know what's the probability. But that's not the question here. So I just explained what this diagram means, but that's not the question they're asking us. They're asking us how many subscribers will each company have in 1 year. Now, of course, we don't know. We're not, we can't predict the future, but we're using a mathematical model. Given what's the expected amount of people, they call that expected value or expected probability. Well, how much based on all the now, by the way, where did they get these numbers from? 10%, 15%, 5%. So these numbers they've gotten just from their data. They see that this is what's been going on for years, and we're assuming, which may be a big assumption, that the trend is going to change. Sometimes things do change for whatever reason, but we're assuming that the trend is going to stay the same. So so here's a matrix. Now let me nice if I can get this all in one shot here. I'm gonna have to make this a little smaller so you can get it all on one. I want to get it all on one page. So as you could see, so let's say, so here's the A column. So if you're in the A column, there is a 15%, there's a 70% chance you're going to stay with A. That's the 0.7 right here. There's a 20% chance you're going to go to B. That's the 0.2 right there. If you're in, there's a 10% chance you're going to go to no satellite. That's the 0.1 over there. And these numbers here in these columns basically are the numbers that we saw up here. The percentages just turned into decimals, and they notice that all the columns, just like all these percentages, we explained how they added up to 1. All these columns add up to 1. And now we have another matrix called the state matrix. 15, 20, 65. Where do these numbers come from? Because we said that in the given, we said that there are 15,000 people have satellite company A, 20,000 are signed up right now at this moment are signed up in company B, which means by subtraction there are 65,000 who don't have any satellite. So that's the story with that. So now, how do we figure out? Well, of the 15,000 people who have A, so there's a 70% chance they're going to stay with A. And of the 20,000 who have B, there is a 15% that they're going to move to A. And of the people who have none, there's a 15% chance that they're going to move to A. So 70% of the 15,000 and 15% of the 20,000 and 15% of the 65,000 are going to go to A. Well, this looks like, like a dot product-y thing, which is basically, screaming matrix multiplication. And that's exactly what we do. Multiply these two matrices, and we multiply the probability, the stochastic, sounds like sarcastic, the stochastic matrix here, and multiply that by the state matrix. And this gives us a list of how many people would probably be in A, how many people are going to have B, and how many people are going to have C. So that means that there are 23,250 people who will be in A, if assuming the numbers, the probabilities hold up, and they're going to be 28,750 in company B, which you see from this matrix. So power, simple, and that's a beautiful thing, matrix multiplication, very simple matrix multiplication. And what's cool about this is that once you have the model, once you have the matrix, then you could use it, from year to year. Of course, assuming that this is all a big assumption, but it's assuming that the trends stay the same, which of course, as we know, in this world is a big assumption. But for now, this is a math class, so in a math class, you always assume things, that's just the way it is in a math class. Now, anyway, suppose we want the same company, the same two satellite companies. This is example 3 now, and we want to know how many people, if the trend continues, which of course is a big if. So how many people will be in each company in 3 years? How many people are going to be there in 5 years? How many people are going to be there in 10 years? Well, all you got to do is just keep multiplying the same matrix 3 times. and that'll predict what's going to happen in 3 years from now. And here you just multiply the same matrix 5 times. Now that will predict what's going to be after 5 years, and here 10 times. And so if you multiply, when you multiply the matrix, the P matrix, that's by the X matrix, which is what we did above. That's what we did in example 2. We got these numbers: 23, 250, 28, 750, and so on and so forth. Well, if I want to know 3 years from now, I just multiply 3 times. So I multiply P to the 3rd power times the matrix X. And if I do that, you're going to get these numbers right here: 30,000 in A, 39,000 in B, and so on and so forth. And 30,000 will have no satellite. Essentially, it had been 65,000. Now it's 30,000. So now what's going to be in 5 years? Well, just multiply the matrix 5 times. Because we're not going to take you through the excruciating process of doing that. And this is an example where you might want to, where one would use a, in industry, I doubt you're going to start doing things by hand. You're going to probably use whatever computer calculators or whatever to do this matrix multiplication. And you're going to get these numbers: 32. So 30. So 32. So 30. Now notice that originally, the company A was originally 15,000 and company B was originally 20,000. So A jumped up in 1 year, they jumped up to 23, and B jumped up to 28. Then after 3 years, A is going to be 30,000, which is double what it originally started. B is going to be 39,000, which is close to double what originally started. After 5 years, 32,000, 43,000. They're both climbing. But look after 10 years. After 10 years, there's not that much from 32 to 33, from 43 to 47. The jumps are not as, it didn't double. It didn't double in the first 5 years. It more than doubled. In the second 5 years, it does not more than double. In fact, it's not even close to doubling. It's So what's going to happen if assuming that the trends stay the same and you just keep on reapplying this matrix, what's going to happen is that it's going to kind of, I guess, level. I don't know if level off is the right word, but it's going to reach what they call a steady state, where it's not really going to change much. And in this case, the steady state, we call it X bar, is 33,000, 47,000, and 19,000. That's the steady state that's going to get reached. And if you would keep on approaching, do this year after year after year after year. Now let's take these numbers and multiply them by a matrix P and see what happens. Well, if you take these numbers and multiply them by a matrix P, again, I'm not going to go through the excruciating multiplication, but if you do that, you basically wind up getting pretty much the same numbers. So if you and try it, you'll see. And that's the steady state. So if the trends continue, then A is going to have 33,000 pretty much forever. B will have 47,000 pretty much forever, and there'll be 19,000 pretty much, forever. Not going to have TV. Anyway, that concludes stochastic matrices. In our next video, we're gonna tackle the subject of cryptography, which is a fascinating topic. And cryptography is, I guess, something that they do on the planet Krypton. I get it. That was a joke. Anyways, we're going to end the video now, and we will see you guys next time.